Welcome to the Organic Chemistry Podcast, or Dr. Brian Lloyd's Scribblecast. Here we offer you organic chemistry lectures and solutions to homework problems. In this solution, we are dealing with a homework problem in bond dissociation energy, where you were given the following reaction and asked to determine, using bond dissociation energies, heat of reaction, or an enthalpy of reaction. In order to do this, we must consider what is happening in the reaction and determine the proper bond dissociation energies to use. Of course, you need a table of bond dissociation energies, and so you may use the table that was supplied in the lecture when you were given this question. Now, to take Cl2 and react it with the molecule ethylene, CH2 double bond CH2, in order to produce the products, the first things we must do is clearly break the Cl-Cl bond and break one of the CH bonds off the ethylene. So in order to make the products, I know I must take Cl2 and react it to produce Cl dot, a radical, plus Cl dot. We utilize homolytic cleavage in bond dissociation energies so that the bond is completely broken and we minimize any interaction, allowing the energy to be determined. Now the values I'm going to write down here are ΔH values in kilocals per mole. Now, when you break a bond, ΔH is positive. You must put energy into the system, and the Cl-Cl bond is 58. So this is a plus 58 kilocals per mole. Likewise, we take ethylene, and we break it down into an ethylene radical, plus H dot. Looks like I better move this 58 over a bit. And if we look on a chart, if we're given a chart that actually shows different alkyl H bonds, we find the appropriate one. If, however, you only given carbon H is a value, you may use that value. This chart, however, gives you a variety of values for carbon H. And you see a CH2 double bond CH hydrogen bond is 108. So this is a plus 108 kilocals per mole. Now, in order to form the products, we now must take the alkene radical, CH2 dot, and a chlorine radical, and make the one product, CH2 double bond CH Cl. And the ΔH for this, a chloro and ethylene, is given as 84, but since it's bond formation, it's negative 84 kilocals per mole. And then the last one, we take H dot plus Cl dot goes to HCl. And that HCl is given as 103, and we're forming the bond, so that's minus 103. So now we add up everything here between those two blue lines. And by adding everything up on both sides of the equation, I should generate the top reaction, unless I've done something wrong. So we've got Cl2 plus CH2 double bond CH2. So that's everything on this side of the arrow. I've got alkene radical, what have we got? I got Cl dot and Cl dot, so it looks like I've got two 2 Cl dots, and it looks like an H dot. So I have all of those things on one side of the equation, and I can draw an arrow. On the other one, I have the CH2 double bond CH Cl plus an HCl. I have the alkene radical. Dot. I see I have 2 Cl dots. And I have, okay, Cl dot, Cl, and an H dot. So now I compare both sides of the reaction, and just like a mathematical equation where there's identical values on opposite sides of the equation, you can subtract both from each side and they essentially cancel. So the alkene radical cancels the alkene radical, the 2 Cl dots cancel 2 Cl dots, 2 H dots cancel, oh sorry, the H dot cancels the H dot, and you're left with what essentially was the original equation. And that tells me my solution is consistent. I've made no mistakes. So now I can add up my delta H values. And I see if I add up the negatives, that's minus 187. If I add up the positives, that's 166. Okay, so I can do 187, 166. Well, that's pretty easy. I get a 1 and a 2, and so I end up with minus 21 kilocalories per mole. This minus 21 kilocalories per mole, is, because it's negative, tells you that this reaction is exothermic and energy is released. So like we're breaking a lot of bonds, forming a lot of bonds, but overall we're getting more energy out by chlorinating the alkene. Thank you very much.